Hi, welcome to Recitation 0, Part B of Introduction to Deep Learning. My name is Omar Khattab, and in this part of the recitation, I'm going to introduce you to Numpy, Python's de facto standard library for numerical and scientific computing. So in this course, and more generally in machine learning and deep learning, you'll be dealing with large volumes of numerical data, typically in the form of matrices and vectors. You'll be implementing various mathematical and linear algebraic transformations on these matrices and vectors, like matrix vector multiplication, for instance. Now, to implement matrix vector multiplication, given a matrix and a vector, you might begin by looping over the entries of the matrix and basically operating at the level of the individual numbers. But as you'll see in this recitation, a better approach would be to vectorize your code. That is, to use an API, like the one Numpy provides, to express your operations at the level of matrices and vectors directly, whenever appropriate. As we'll see, vectorized code can be much more concise, and hence less bug-prone, than nested for loops. But it can also be much faster, because you'd be relying on Numpy's low-level efficient implementation for the numerical computation, rather than using Python for loops for that purpose. Okay, let's begin with a simple example. We're going to compute wx plus b for matrix W and vectors x and b. We will first have a look at a naive implementation in Python, which we will then vectorize using the Numpy API. So for the naive implementation that uses nested for loops, our vectors will be Python lists, and our matrix will be composed of nested lists, as you can see here. So W is a 3x3 matrix. So this is the first row, second row, and third row. And X and B are initialized, as you can see. We will also create a zeroed output vector, Y. And now to compute the matrix vector product, we simply loop over the rows of the matrix, then loop over entries in the row. So we have a two-level nested for loop here. And then we just multiply and add. For the vector addition, we loop over entries in the output Y and add to every entry the corresponding entry from the vector B. We get the desired output. But now let's have a first look at Numpy. We will vectorize the above example using the Numpy API. First, we import the library. We import it as NP, which is a standard practice. We then create our first Numpy arrays. W is a 3x3 matrix, which we initialize from essentially the same matrix W that we had using nested Python lists. X is a 1D vector, again initialized from a Python list. And B is initialized using Numpy's array creation API. So it's a vector with 3 ones. Now for the actual computation, the matrix vector product is really simply expressed using w.x, which returns this vector. And vector addition is as simple as using the overloaded plus operator. Now, let me note something here. Numpy vectors are essentially just lists of numbers. As such, they're not really row vectors or column vectors per se. Each vector works as either. If you really need a row or a column vector, you can construct a 1 by n or an n by 1 matrix, respectively. Now we're ready to discuss Numpy's main or core data structure, the multi-dimensional arrays. Most Numpy's code, if not all of it really, operates on n-dimensional arrays. So this can be a vector in 1 dimension, a matrix in 2 dimensions, or really any n-dimensional tensor. So here we can create and fill tensor T of dimensions 2 by 3 by 4 with random floating point numbers between 0 and 1, following a uniform distribution. Indexing works as you'd expect. So this gives us the first entry along the first axis in T, which is this matrix, this 3 by 4 matrix. We can inspect its shape and the data type of the entries. In order to allow vectorization effectively, Numpy arrays have fixed uniform shapes, like we had in this case, and have a fixed data type for the entries. So this can be a 64-bit float or a 32-bit integer, etc. Here we create a matrix X, which is full of this value and has dimensions 4 by 3. The data type is specified to be 32-bit integer. Again, we inspect the shape and the data type, and they are as expected. To compute a matrix multiplication, we use the same overloaded operator, dot, and we get the output of W times X. Clearly, if we had X being full of zeros, so as an array of zeros of the same shape as X, expressed in this form, we would expect the matrix product Wx to be all zeros. And clearly, indeed, this matrix product is equal to the 3 by 3 matrix of all zeros. So now let's discuss basic element-wise operations in Numpy. This is where you start noticing more and more the capabilities of the Numpy API. So we can create this vector y, which has entries from 0 to 9 inclusive. That's the same thing as creating this Numpy array and initializing it with this Python range. So we can print both, and we see they're the same. So checking for equality, you might be tempted to write this kind of code. And indeed it works, but what it did was it gave us an array of 10 true values. So really what was happening was Numpy applied the equality operator element by element, and it figured out that every pair of corresponding elements in y and this array are equal. So this is going to form the basis for the next few examples. Numpy simply applies the operation element by element or element wise, and it does so efficiently. So this adds 1 to all the values in y. This multiplies each of them by 10. This adds 1 to each and then squares. Now this is a little different. Here we are adding every value in y to the corresponding value in the other vector, which is also y. So this is similar to doubling the values, multiplying them by 2. And you see the trend from here. Here we're computing the square and then taking the square root. So we're getting y back, except that the values have been casted to floating point numbers. And we also have the other convenient math functions like minimum, maximum, standard deviation, sum, product. Feel free to check the references for further functions that you're going to find useful. The links are provided at the end of the notebook. And now we'll discuss indexing Numpy arrays. Let's execute this line, which saves some array to a file. Now we can load T, a tensor, from that file and inspect it and its shape. So this is one other way of obtaining and initializing Numpy arrays. It's probably the most useful to start working. So you might have a data set and it's saved in a file, and that's how you load it. Now, as we saw above, we can simply access an element in the array like we'd access Python lists, and this gives us this matrix. We can also access a specific numerical entry, a scalar, by specifying its position. So it's going to access 16. This is a more efficient syntax for accessing Numpy arrays that is, in terms of behavior, equivalent to this one, except that this one has to return this array first, which involves a copy operation, then extract this array, and then return this scalar. Here we're directly indexing. And Python style slicing also works as expected. So if you wanted to focus on this matrix, take only these two rows and then extract these two subcolumns, this would do it. And lastly, we can do some kind of conditional indexing where we extract specific entries from the tensor or from the n-dimensional array. So if you want to keep only the entries which are divisible by 4, we can find the entries where this applies and then index T with the output. So if we look at the output of this, we see that it's true in exactly the positions where the value is divisible by 4, and indexing into T with this is going to return to us the entries where the Boolean value here was true in the same order. Now let's discuss a quick example that uses what we saw in terms of indexing and what we saw in terms of multidimensional arrays. Let's create W, a matrix of dimensions 4 by 4 that has entries between 0 and 9 inclusive. Again, you know, the above operations generalize to higher dimensional arrays, so we can do these element-wise exponentiation and division. Now let's create an array called mask, which is filled with ones, has the same shape as W2, except that we want to set the second row to 0. So this is using something that's called broadcasting, which we'll discuss later in Numpy. But intuitively, it's just setting the second row to all zeros. Now if we compute the element-wise product of W and the mask, we can expect all these rows to stay the same and the second row to be zeroed out, which is exactly what you get relative to this. We've seen element-wise conditionals or comparisons, before. So this is true exactly for the entries that are bigger than 5. So let's say we want to clip the values at 5, so that all values are either smaller than 5 or equal to 5. One way to do so would be to index into the positions that are bigger than 5 and set them to 5. And you notice that all the values now are at most 5. And that's the same thing as using the minimum function with the argument 5 in Numpy, which would match element-wise with our W3. The next topic we'll discuss is computation along axes. So again, we can create this random matrix. We've seen the sum before of all entries. But we can also compute the sum row by row, so we can add up all the rows We can also add up all the columns by specifying the axis to be 1, and we can find the maximum along columns, and we can also find the position of the maximum argument in every column. So the maximum here is at position 1, this is also position 1, and this is position 2, as we get in this output. Next is combining arrays. We're going to discuss two Numpy operations, stacking and concatenation. Let's create three vectors, A, B, and C, which are of 5 elements each, filled with 1, 2, and 3 respectively. Say we want to stack A, B, and C next to one another as columns of a matrix. Numpy provides the stack function, which takes an axis argument that specifies the axis that if we index, we get one of the input arrays that we provided. So if we stack A, B, and C along the second axis, which is axis 1, this is the output. And if we index axis 1, we get, in this case, the vector B, which is the second column here. Now say we want to apply a simple transformation to B twice, and then concatenate the outputs so that we get a wider matrix. That's what the concatenate function does. You're probably familiar with the transpose operation from linear algebra. You can simply use the matrix B. So if you say B dot uppercase T, that transposes your matrix, which behaves exactly as expected. Notice that the shape is transposed. But there's also the reshape functionality in Numpy, which keeps the data in its original row major-like order, but allows you to access it and use it under a new shape. So here we're reshaping B, which was a 5x3 matrix, so that it looks like a 3x5 array. And you notice that the original order is kept the same, but the new shape is 3x5. Next is broadcasting, which is another concept in Numpy that enables elegant vectorization of code. Broadcasting is basically the way Numpy allows operations to occur between arrays that do not have strictly compatible shapes. But where the smaller array, which is the one with a smaller number of dimensions, or where some axes have dimension 1, can sort of be stretched to allow the operation that you would intuitively expect to actually occur. We've already actually seen an example of broadcasting where we added a scalar, it was the value 1, to a vector. The result was another vector where every entry was increased by 1, as you probably expected. There's a few examples here. Please go carefully through them to understand the way broadcasting works in Numpy and the conditions for it to be allowed. And lastly, you will need to deal with external data files, either as input or output from your Numpy programs. So these examples describe saving and loading a single Numpy array, as well as saving and loading a dictionary of Numpy arrays. And these are a bunch of references you'll probably find useful. So this was a brief introduction to some core Numpy functionalities for Introduction to Deep Learning. If you have any questions, as always, please feel free to post on the course page on Piazza, and definitely try to go through the examples and snippets of code provided in this notebook. Thank you very much.